Good evening. That worked. So, hello. I want to welcome all of you to the annual Dan E. Christie Mathematics Lecture. This lecture series was established in memory of Dan Christie by his family, friends, colleagues, and former students. A native of Dover-Foxcroft, Dan graduated from Bowdoin in 1937, and after receiving his doctorate from Princeton, returned to Bowdoin in 1942, serving in the math department for the next 33 years. The author of two textbooks, one in vector mechanics and the other in point-set topology, Dan was the Wing Professor of Mathematics from 1965 until his untimely death in the summer of 1975. During the 1960s, Dan was the director of Bowdoin's Academic Year Institutes for secondary school teachers, as well as director of Bowdoin's Advanced Science Seminars, a series of NSF summer research programs in mathematics. Dan also worked extensively for the Mathematical Association of America. He was a founding member of its Northeastern section, served on many MAA panels and committees, and was elected to 2 terms on the Board of Governors. In recognition of Dan's MAA contributions, there is another annual lecture series named in his honor, this one delivered each year at a Northeastern sectional meeting. Dan believed that no one was truly literate unless they were aware of what mathematics was and what living mathematicians were doing. It is thus fitting that a lecture series like this, featuring exceptionally accomplished mathematicians and scientists explaining important work to a general audience, be named in Dan's honor. It is my great pleasure today to welcome mathematician Art Benjamin to Bowdoin College. Professor Benjamin visits us today from Harvey Mudd College, where he is the Smallwood Family Professor of Mathematics. Professor Benjamin received his undergraduate degree from Carnegie Mellon University and his graduate degree from Johns Hopkins University. This afternoon, I introduced Professor Benjamin as a distinguished mathematician and highly acclaimed teacher. Tonight, we are here to explore his alternate identity. For us, he is Professor Art Benjamin, mathemagician. The Los Angeles Times described him this way: he talks like a performer, acts like a magician, and multiplies faster than a calculator, which makes him sound like someone who could either talk you out of an exam, make it disappear, or take it for you in less than 3 minutes. Very useful to have around, especially this week. Professor Benjamin is a professional magician and has performed his Mathemagics show all over the world in a wide variety of venues. He has authored several books, including Secrets of Mental Math and 4 DVD courses for the Great Courses. He has received national awards for his research, writing, and teaching. He is the winner of the National Teaching Award from the Mathematical Association of America and was listed by Princeton Review as one of America's top 300 professors. His newest book, published this fall, is called The Magic of Math: Solving for X and Figuring Out Y. It's good to see that even if you laughed at that this afternoon, you laughed at it again. Dr. Benjamin has appeared on many television and radio programs, including The Today Show, CNN, and The Colbert Report. He has been profiled in the New York Times, the LA Times, USA Today, Scientific American, Discover, Omni, Esquire, People, and Reader's Digest. He has given 3 TED Talks, which collectively have been viewed over 10 million times. In 1997, Dr. Benjamin applied his talents to the game of backgammon and won the American Backgammon Tour. In their Best of America issue, Reader's Digest recently called him America's best math whiz. Please join me in welcoming mathematician Professor Art Benjamin to Bowdoin College.
Thank you. How great to see so many people out here on a Thursday night for a math talk. It warms my heart. Well, good evening, ladies and gentlemen. My name is Art Benjamin, and I am a mathematician. What that means is I combine my loves of math and magic to do something I call Mathemagics. But before I get started with anything too mathematical, I thought I'd begin with a magic trick. It has nothing to do with math, really. It's just a really cool trick. But for this, I'll need a volunteer to assist me. Someone here I do not know. And, all right, how about you? What's your name?
Isaac.
Let's give Isaac a nice round of applause. Isaac, before I begin, have we ever met before?
No.
You seem proud of that. That's good, because Isaac, I'm going to show you and everyone here a card trick that has never been seen before. Never been seen before because no one can see the cards. Isaac, if you would, pick a card, any card at all from the deck. Good. Look at the card, show it to everyone, but do not let me see it. All right? I will shuffle the rest of the cards so you see they're not in any particular order. Oops. What's that?
It's not on.
Oh, it's not on. I'm on, but the mic isn't. Okay, so you've shown the card to everyone? Wow. Okay. All right, make sure I can't see it. All right, so I'll shuffle the rest of the cards so you see they're not in any particular order. I'd like you to place the card back inside the deck, but just to make it interesting, turn the card upside down first. Upside down. Good. Notice all the cards are face up, except for Isaac's, which is face down. Now watch carefully, as this took me years of practice. Watch, watch, watch. As I make the deck of cards disappear from my hands, reappear, it gets better, reappear inside of this box, a box which only moments ago was empty. Trust me. Now I realize, Isaac, what you were doing a moment ago was just a figment of your imagination, but what was the card, for that brief second at least, that you imagined that you selected? Isaac, what card did you imagine?
A 7 of diamonds.
7 of diamonds. That's amazing because you'll notice in this deck that one card, and only one card, has been turned upside down. Would you be so kind as to show everyone the upside down card? The 7 of diamonds. And let's give Isaac a nice round of applause. Thank you, Isaac. While you're trying to figure that one out, I have another question for the audience. By any chance, did anyone happen to bring with them this evening a calculator of some sort? Wow, that was a psychic in the audience, too. I'm very impressed. If you have a calculator with you, it could be on your phone or an honest-to-goodness calculator. Raise your hand, raise your calculator. I need a few people to help me out here. I see, okay, I see one. Oh, would you help out with that? Okay, so there's something there. Yeah, I got it. All right, so we got, all right, 1, 2, 3, and 4. Would the 4 of you bring out your calculators, join me up here on stage. Let's give these volunteers a nice round of applause. Come on up. Fantastic. All right, great. One more round of applause for our brave volunteers. Now, since I have not had the chance to work with these calculators, some actual bona fide calculators, you don't see those so much these days, I want to make sure that they're all working properly. Would somebody get us started by giving us a 2-digit number, please? 26. And another larger 2-digit number? 94. Multiply 26 times 94. Make sure you get 2,444 exactly, or the calculators are not working. Are all your calculators working? 2444. Give them a round of applause. Now, I notice that took some of us a little time to get the answer, and that's okay. I'll give you a shortcut for multiplying even faster on the calculator. There's something called the square of a number, which most of you know is taking a number and multiplying it by itself. For instance, 5 squared would be 25. 6 squared would be 36. 73 squared would be something bigger. Right. Now, most of your calculators have little shortcuts for squaring numbers, and if you know them, go ahead and use them. If you don't, you'll just have to do it the long way, like 26 times 26. What I'm going to try and do now is to square in my head 4 2-digit numbers faster than they can do on their calculators, even using the shortcut method. What I'll ask is 4 people here. How about in the first row? 1, 2, 3, 4. Each yell out a 2-digit number, and if you would square the first, the second, the third, and the fourth one, I will try and race you to the answer. So quickly, a 2-digit number, please. 76. Okay, next. 83. Next. 92. Great. And one more. 57. Would you call out your answers, please? 5776, 6889, 8464. Give them a round of applause. Let me try to take this one step further. I'm going to try to square some 3-digit numbers this time. I won't even write these down. I'll just call them out as they're called out to me. Anyone at all call out a 3-digit number. Anyone on our panel verify the answer. If I get the answer right, give me a thumbs up. If I make a mistake, let me know, and I'll try and fix it. A 3-digit number, anyone? 679. Is that 461,041? Yes, good. Another 3-digit number, sir.
223.
223 is 49,729. 49729. Good. How about another three-digit number? 327 is 106,929. Yes, good. One more three-digit number. Go ahead. 411 is 168,921. Thank you very much. Let me try to take this one step further. I'm going to try to square a four-digit number this time. I'm not going to beat you to the answer on this one, but I will try to get the answer right. To make it a little more random, how about four people in this row? How about 1, 2, 3, 4? Each call out a single digit between 0 and 9. That will be the four-digit number that I'll square. 6, 8, 9, 7. This will take a little bit of time, so bear with me. 47 million 568,609. Good. Thank you very much. Now, I would attempt to square a five-digit number, and I can, but unfortunately some calculators cannot. What can you do? But so since we've reached the limit, I know yours can though, yeah, I'll talk to you later. Since we've reached the limits of our calculators, I'd like to conclude the first part of the show by trying something a little trickier. Let's take the last number on the board here, 3249. Would you each enter 3249 on the calculator? And instead of squaring it this time, I'd like you to take that number and multiply it by any three-digit number that you'd like. But don't tell me what you're multiplying by, just multiply it by any random three-digit number. So you should have as an answer either a six-digit or probably a seven-digit number. How many digits are in your answer there? 6 or 7? 7, 7, 7, 7. Is there any possible way that I could know what seven-digit numbers they have? Say no. No. Good, thank you. But I will attempt the impossible, or at least the improbable. What I'd like each of you to do is to call out for me any six of your seven digits, any six of them, in any order you'd like. One digit at a time, I shall try and determine the digit you've left out. So starting with your seven-digit number, call out any six of them, please.
2, 5, 2, 4, 4, 3.
Did you leave out the number 7?
Yes.
Good. That's one. I love you. I want you to all my shows. You have a seven-digit number. Any six of yours, loud and clear.
4, 5, 5, 5, 6, 2.
Having a little trouble with this one. Let me get back to you. Don't forget it. You've got a seven-digit number. Any six of yours, really scramble them up.
Okay. 6, 0, 5, 5, 8, 3.
6, 0, 5, 5, 8, 3. I'm having some trouble with this one, too. Don't forget your number. I'll get it. And finally, you have a seven-digit number. Any six of them in any order.
0, 8, 7, 6, 6, 8.
Ooh. Did you leave out the number 1? Okay, good. I've got 2 here, 2 to go. Do me a favor, both of you, if you would. Concentrate on the digit you left out. Doesn't do any good. It just looks dramatic. And yet, I seem to be getting a lot of nothing. You didn't leave. Which of you left out a 0? No wonder I was getting a lot of nothing. And let's give all 4 of these people a nice round of applause. Thank you very much. Thank you. For my next number, I'd like to present something that we mathemagicians refer to as magic squares. For those of you unfamiliar with these, they're kind of like Sudoku on steroids, and you'll see what I mean by that in just a moment. Now, I've done such an extensive study on magic squares that I'd like to create one for all of you right before your very eyes. But for this, I'll need another assistant, someone here I do not know. And let's see, I do not know you. What's your name? Let's give Eloise a nice round of applause. Come up here, Eloise. Adorable. Now let's see, Eloise, spelling was not my best subject. Is it E-L-O-I-S-E? Yeah. Okay, good. Did I get it right there? Okay, Eloise. Let me ask you another question, and I may need your parents' help on this. So, Eloise, what is your birthday?
May 25th.
And you have May, that's 5/25th, and what year?
2008.
Excellent, 2008. So, Eloise, now if we were to add the numbers in your birthday together, let's see, 5 plus 25 is 30, plus 20 is 50, plus 8 is 58. So, Eloise, 58 becomes your magic number. What I'm going to try and do now, Eloise, is to fill out this box in such a way as to get your magic number appearing here as much as I possibly can. This will take me a couple of seconds, so bear with me here. I think that works. Eloise, would you choose any row? Row number 1, 2, 3, or 2, 3, or 4? Which would you like? 3. Okay, class, together. 9 plus 21 is 30, plus 24 is 54, plus 4 is 58. Those were 5, 30, 50, 58, 19, 28, 32, 58, 25, 28, 38, 58. Would you choose a column, Eloise? 1, 2, 3, or 4? 2. All right, class. 25 plus 9 is 34, plus 21 is 55, plus 3 is 58. The others were 5, 24, 33, 58, 20, 24, 48, 58, 8, 34, 38, 58. How about that? Now, Eloise, I'm not through with you. I decided since this was your magic square, based on your birthday, at no extra charge, I would give you these diagonals as well. Check it out here. 25 plus 21 is 46, plus 4 is 50, plus 8 is 58, 5, 14, 38, 58. But I didn't stop there either. I decided since this was for Eloise, wouldn't it be great if we could get these 4 in the center to add up as well? Check it out here. 9 plus 4 is 13, plus 24 is 37, plus 21 is 58. But did I stop there? Did I stop there? No, Eloise, you may have noticed I put a little extra attention in that corner. I did that so I could get these 4 squares. 5 plus 25 is 30, plus 9 is 39, plus 19 is 58 to add up. And I figured, heck, as long as we got that group of 4, let's have a party. We may as well get this group of 4, 20, 28, 54, 58, 9, 30, 33, 58, 24, 28, 48, 58. But did I stop there? No, I said Eloise wouldn't be happy unless we got this group of 4, 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 this group of 4. And I have to, in fact, and by an amazing coincidence, and I don't usually get this, even this group of 4 and that group of 4, that's a very special magic square. And to make it extra special, Eloise, if you look at the numbers in the 4 corners, not only do they add up to 58, but if you look at them closely, we have 5, 25, 2008. I gave you your birthday twice because I thought you'd like that. So please keep this as a souvenir from me. And let's give Eloise a nice round of applause. Thank you, Eloise. There you go. You are welcome. I'll even sign it afterwards, so don't forget. Okay. Hey, speaking of birthdays, by any chance, does anyone here happen to know the day of the week that they were born on? If you think you know your actual birthday, raise your hand. All right, how about this gentleman here? What year, if I may? 96, and what month? November what? 28th. Was that a Thursday? Thanksgiving, yeah. How do we remember that? Who else? How about yours? What year? 94. And what month? October what? 13th. Was that a Thursday also? 2 Thursdays in a row. What are the odds? No, really, what are the odds? 1 in 49, but that's another story. How about somebody else? Yes, what year? 1997. And the month? April what? 20th. Was that a Sunday? Yeah. And how about yours? What year? 72. And the month? February. Let me think about this one. February what? 18th. Was that a Friday? Thank you very much. Let's see, Eloise, you say you know yours. All right, let me see now. Let's see, your birthday, we all know that, was May 25th, right? 2008. Was that a Monday?
Yes.
Excellent. It was, what's that? And it changes almost every year. It was Memorial Day, huh? Oh, how wonderful. Do we have anyone here who does not know their day of the week but always wanted to find out? Let's see. All right, we'll do yours. Now, of course, if you don't know what it is, I could just make up an answer and you'd probably believe me. But luckily, there are apps for everything these days. I'll ask one of you here to help me. All you have to do is type in the year, and the rest is pretty clear. So here, why don't you take that? So what year, first of all? 94. So type in 1994, and what month? Press the August button, look at the calendar. It's August what? 27, I think, is a Saturday. Can you confirm? It is a Saturday. I'll tell you what, as long as you have the app with you, let's try something even more challenging. The app will go as far into the past as 1600 and as far into the future as 9,999. So give me a year, you can give it yourself, that's between 1600 and 9999. What year would you like? 1643. Okay, 6043. Let me think about that. And someone else, give me a month. What month would you like? September. September what? 17th. Was that a Thursday? It was a Thursday. And it was cloudy, I think. Thank you very much. Thank you. Anyone else who wants to find out their birthday, see me after the show, and I'll be more than happy to tell you. Now, folks, if I were performing for a different sort of audience, like, say, at the Magic Castle in Hollywood, as I sometimes do, I might follow this up with other feats of magic and mind. But for an audience such as this one, I actually prefer to break the magician's rule and explain to you most of what you've seen me do up here and more. In fact, I'd like to conduct the rest of this program, the next 30, 40 minutes or so, very informally, so feel free at any time to interrupt me with questions, even if it has nothing to do with what I'm talking about. It's more interesting that way. In fact, I've got hours and hours of stuff I could show you, but far less than that time to be here, so I'll start taking your questions now. Yes, sir, you get the first question. How do I do the card trick? All right, it's good to get that one out of the way first. All right, if everyone asks me at the same time, how'd you do it? I did it very well. That is the only part of my show I can't reveal. I would get kicked out of the Magic Castle if I taught you that one. But anything else, all the rest are based on mathematics. I'm more than happy to explain. Or any other kinds of questions, mathematical mysteries you may have. Yes, please. What's the maximum limit that I can do or that others can do? I'm not by any means, fastest or largest problems out there. The biggest I can do in a public show is multiply two 5-digit numbers. My plan is to square one for you by the end of the night. All right, but I'll save that for the big finale. The biggest I've tried without, not in front of a big audience would be like multiplying two different 6-digit numbers. That is my limit, but it takes me a little too long and I'm a little too error prone to try that one on stage. But that's sort of the biggest I do. But I mean, I've met other people who've done these mental abacus methods who could visualize an abacus with like 20 poles and, these numbers, 19-digit numbers are being called out, and the people are just adding them up on their mental screen, and that's well beyond anything I could ever do. Yes, please. So let's talk mental math here. So a few basics. First of all, if there's only one thing you remember about all the mental math that I do, is this. I do all of my calculations from left to right. And that's the opposite of how you do it on paper, right? On paper, we normally go from right to left. We do the ones, the tens, the hundreds, the thousands, and so on, but that's backwards. We read numbers from left to right. We pronounce numbers from left to right. We say 3,249, not 9 and 40 and whatever, 203,000. That's hard, right? And I claim that if you want to calculate quickly, you need to calculate from left to right. Let me start by showing you the squaring method that I use for two-digit numbers. If you're interested, I'll show you how we push it up to three-digit numbers and higher. Give us a two-digit number to get started. 70. All right, let's make the first one smaller. I don't know. No, I should have said a small one just as our first example, and then we'll do 74 as a second example. Give us a two-digit number. 18. Okay. Now, I do have to confess, I've been squaring numbers for such a large fraction of my life now that probably all the two-digit squares have become memorized. Not intentionally, but I just know. Maybe some of you know. 18 squared is 324. Okay, so let me show you the method, though, that I use for squaring. So 18 is not a bad number to multiply, but what number close to 18 is much easier? 20. So I go up 2 to 20, and to balance it, I go down the same distance. I go down 2 to 16. So the first part of my calculation is I do 20 times 16. Now, if you double 16, what do you get? 32. So 20 times 16 is 320. Almost there. All you have to add to this is the square of the number you went up and down. You went up and down 2. 2 squared is 4, and there's your answer, 324. Let's do a couple more examples. I want to make sure everybody gets good at this. You said 74 a few minutes ago. So let's see how that would go here. That's a trickier one. In fact, it's about as tricky as they come. So let's see, 74, now the nearest easy number would be 70. 75 is not bad, but I like numbers that end in 0 because I like zeros. So I go down 4 to 70. To balance it, I go up 4 to what? 78. Now we do 70 times 78. I'll ignore the 0 at first by doing 7 times 78, and we'll do it left to right. Let's do it together. 7 times 70 is 490. 7 times 8 is 56. 490 plus 56 is 546. 546. With the friendly 0, that's 5,460. Almost done. All we have to add to that is what? The square of 4, which is 16, to get 5,476. Okay, and that's exactly what I'm doing. Here, now it's your turn. I'll give you a problem. See if you can do it. When you think you have the answer, raise your hand, but don't say it out loud. Give everyone a chance. I want everyone to have at least 10 seconds to do this problem, all right? In your head, I want you to try to square the number 97. Don't say it, think it. When you think you have the answer, raise your hand. Think of what you'll go up to, what you'll go down to, multiply, and add. What did you get? 9409. Give him a round of applause. Well done. Think of what, and how did we do this, right? I hope you went up 3 to 100, down 3 to 94. 94 times 100 is 9,400 plus the square of 3, not the square of 7, but the square of 3, which is 9, to get 9,409. Give him another round of applause. Well done. So once you get quick and good at squaring two-digit numbers, you can then attempt going higher, like three-digit numbers. Give us a three-digit number, sir. I'll try and show you how to do that one. Yeah. 245. This is one that maybe we all can do. All right. So now before I square 45, what makes this problem especially nice is that it ends in 5. Numbers that end in 5 are really nice. In fact, here, let me show you with a two-digit example, 45 squared. Think of how we do it. We go down 5 to 40. Therefore, we go up to what? 50. 40 times 50 is 2,000. So what's the answer here? 2,025. Okay, very nice. Now, we're going to square 245. Now, when I square a two-digit number, I round it to the to the nearest easy multiple of 10. Like with 45, I rounded it to 40. With a 3-digit number, I rounded to the nearest 100. So 245, I'm going to go down 45 to 200, up 45 to what? 290. 200 times 290. Now I've got 3 zeros here. 2 times 29 is 58. 40 plus 18, 58. So that's 58,000. Add to this what? The square of 45, which is staring us in the face. 2025. So what's the answer? 245 squared is 60,025. And that is exactly how I'm doing it. I don't have that answer memorized. I'm really calculating it, and I'm calculating it exactly that way. Now, you'll have trouble doing this yourself. Don't try this at home until you get really quick at the 2-digit squares. Because if you do, you might make it this far, 200 times 290, and get 58,000. You might get this far and do 45 squared to get 2,025. But then you say, okay, now I add that 2,025 to it's gone, right? By the time you've done this, unless you can do 45 squared so quickly that you don't have time to forget this number, by the time you get this, you may have lost that, right? And I run into that problem once I start squaring 4-digit numbers, and I'll show you how I get around that one later. But let me take a few more questions before I jump into the memory tricks. Yes, sir? I can make a magic square no matter what the birthday was. If the birthday has some small numbers in it, I might have to resort to a -1 inside the square. So I might have to get, if someone was born January 1st, 2000, I'm going to have a negative number in there. But otherwise, yes, it works all the time. Yeah.
So in your magic square, I noticed that in the top 2 lines you had from the first line to the second line you had subtracted 1 from 2 of the numbers and added 1 to 2 of the numbers.
The numbers are all close together. That'll always be the case. So you want to see how I do the magic square? I wouldn't show you the card trick, but I will show you the magic square. Now, there's a reason magicians don't freely reveal their secrets. It's because we've all made that mistake before. We expect, we explain a magic trick and we never get the reaction we want. We want people to say, wow, that's clever, you're good, but you never do. I mean, how have you responded most of the time that someone's explained a magic trick? Oh, yeah, that's dumb. I thought you were good, but I just wasn't paying attention. So I will show you how I did the magic square, but just remember how impressed you were before I gave you the explanation, okay? Now, shall we do your birthday this time? Would you like us? So you can stay in your seat, but what is your birthday? May 20th, okay. Yeah, I almost said, wait a second, didn't I do this one already? May 20th, and 2006. Eloise, I want you to say something like every 5 minutes because it just brings up the audience here when we hear your voice. Okay, so May 20th, 2006. And now, if you were born in the 1900s, I don't typically write, like if you were born in 1997, I don't go 19 and 97. I'll just use 9 and 7 for 97. I won't use the 19 in there. But for birthdays in the 2000s, because I don't like too many zeros in it, I don't like to have a 0 here. I write it this way. Okay, now the first step in creating the magic square, and it's an important one, is you have to add these 4 numbers correctly. Because if you make a mistake there, there's nothing you can do. So let's see, 20 plus 20 is 40, plus 5 plus 6 gives me 51. I write it nice and big for everyone to see, including me. Now, because you've seen the trick before with Eloise, we know that not only does the birthday appear in the top row, it's also in the four corners. So what number will go here? 20. All right, that comes from there. And what number is going to go there? That's the first number I write down. And what number goes there? 20. But that's the last number that I write down because I like to keep it a surprise. Okay. Next, and now I go up the diagonal. I always solve it in the same order. I go to this square here. And you can put any number you want here, but the best number to put in to avoid negative numbers, the best number to put in here is this number plus 1. And so everyone born in the 2000s, this number is a 21, because that's a 20, that's a 21. Okay, next, I go up the diagonal. Now, you know that the sum of the diagonal has to be 51, and I have 3 of the 4 numbers already. So it becomes like the easiest Sudoku you've ever tried, because 20 plus 21 plus 6 is what? 47. So what does this have to be to get us to 51? 4, and that's what I write. Next, you recall with Eloise's square that this group of 4 is also going to add up, and I've got 3 of those 4 numbers. 20 plus 6 plus 4 is 30, so what number goes here? 21. Then here, 20, 20, and 4 is 44, so that means this one has to be 7. And here, with this group of 4, 27 and 5 is 32, that's going to be 19. In fact, it'll always be 19 with this 21. Okay, now you might remember I said with Eloise's magic square I got very lucky because this group of 4 and this group of 4 added up. That's extremely rare, less than 5% of the time. So normally this won't add up, this won't add up. However, the way the algebra works, these 2 numbers are equal and those 2 numbers are equal. So I just slide this 7 down and that gives me a 51 over in this column. Now I go to these 4 in the middle. 21, 7, and 4 is 32, which makes that a 19. 21, 20, and 7 is 48. That makes this a 3. 21, 19, and 3 is 43. That makes that an 8. Your brain's tired from all the adding and subtracting, so I save the easiest for last. This number is going to be what? 4, just sliding it down. And this number is going to be what? 20. And that's the secret of the magic square. Thank you very much. Now, to answer your original question, if you started, and I won't do the algebra here, but if you started with A, B, C, D, and you look at everything in the square, they're all within 1 or 2 away from A, B, C, and D. So the fact that the second row looked a little bit like the first row is no accident. So yeah, everything in the square, now that you look at it, is 1 or 2 away from 5, 20, or 6. So but that's the way the algebra works. Speaking of algebra, I meant to do this earlier with the squaring that I showed you, right? I mean, I showed you how it worked, but I wouldn't be doing my duty as a mathematician without quite seeing why it worked. So let's just give it 1 minute of algebra here. If I square the number A, what do I do? Like when you squared the number 97, you took A and you went up some distance D. You take A minus that distance D, multiply them together, and what do we add to that? D squared. And is that going to work? Well, A plus D times A minus D is A squared minus D squared. When you add the D squared here, the D goes away, and you're left with A squared. So I don't think of the algebra as I'm doing the problem, but it's comforting to know that this means that it's always going to work. Okay, so that's good for that's why I like algebra. Other questions? What else would you like to know here? Yes, sir.
How many numbers would you need to put, like, for someone who gave you 2 magic squares?
Would say that
Could you make a magic square with, like, fewer numbers? Say if someone gave you, like, their year and their month.
I'll tell you what I'll do. This is not part of my normal repertoire, but it's something that I've always been tempted to do, and since you asked that question, what's the right number here? I'm not going to do it based on a birthday, but I'll ask random people for random squares. So you can start. What square do you want? If the squares are numbered 1 through 16, which square should I use first? 8. That would be 1, 2, 3, 4, 5, 6, 7, 8. This one here. And what number would you like inside it? 25. Okay. And let's create another one. Which square would you like? From 1 to 16, which square would you like? 17. Not 17. That would be over here. What's that? 5. Okay. 1, 2, 3, 4, 5. And what number would you like inside of it? Let's keep the numbers, say, between 1 and 20. 7. Okay. And how about one more? Eloise, since I haven't heard your voice in 5 minutes, pick a number from 1 to 16. 12. Okay, that would be over here. And a number to go inside it, say between 1 and 20. 6. Okay. And finally, let's create a total. What total would you like here? 42. Hey, it's a good number, 42. Life, the universe, and everything, right? Okay, 42. Okay, so I can't ask for 4 numbers and a total because you might have chosen the 4 numbers on top and a total that was different. So the best I can get away with is 3 numbers and a total. And let's see here. I wonder if this is going to be a problem. I've never thought of this before. And I think I have a couple degrees of freedom here, but I'm pretty sure this number here is going to have to be 4, because I think these 4 are going to have to add up. And it's rare that I have 3 out of 4 that are on a rectangle. I'm pretty sure it's going to have to be a 4, but I'm not even going to dare start that way. I think I have some flexibility. Let's take one more number. I'm going to say go here. Give me a number from 1 to 20. 8? Okay, so I'm going to, oh, you know what? Yeah, okay, that's fine. You'll say 8? I like 8. All right, I might get negative numbers in here, but now that we've chosen 8, I'm forced to make this column here a 3, right? And what else am I going to try to create? I think because of the 3, 25, and 7, these add up to 35. I think I have to make this number a 7. I'm going to pick another number at random. I'm going to cross my fingers here. Give us one more. I'll put a number here. What number would you like? Not say between 1 and 10. 9. Okay, so let's see how this works. Cross my fingers. All right, now I'm hoping everything is forced. 25 plus 7 plus 9 is 41. That makes that a 42. 3, 25, and 1 is 29. That makes that a 13. 13, 9, and 1 is 23. That makes this a 19. Is that adding up? Good. Okay, then this diagonal, 7, 9, 8, is 24. That makes that an 18. This is 18, 9, and 1, which is 28. That makes that a 14. Uh-oh. 14, 7, and 9 is 30. That makes that a 12. I'm getting nervous. 7, 7, and 12. Did I make a mistake somewhere? 7, 7, and 12 is 26. That makes that a 16. And I screwed up. So I am... As I said, it's not part of my repertoire. But so the answer is you could go 3 numbers and a random location. Did you catch me making a mistake in there? Yeah. Is not adding up to 42, yeah, and nor is this diagonal. So as I said, I messed up. I don't know where I went wrong, but anyway, yeah. Slided the 6. This one here. Oh yeah, but this one is not based. That was only working when I had 4 numbers up there on top, A, B, C, D. So anyway, it was a worthwhile experiment, but it failed. I'm not gonna try and continue that. So let's do other questions. Yes.
Kind of related to that.
Yeah. Okay.
You said that you screwed up, but it's possible that just the numbers don't work. I mean, we gave random numbers.
Yeah, I'm not sure if the problem came from the fact that I got 3 of the 4 numbers on this rectangle, and I may have, I can choose 1 or 2 new places at random, but I have to be a little careful. I think, for example, that I had to have a 4 here for this to turn into a magic square. And when I saw that I didn't get a 4 there, there might have been other places where I was forced to pick a certain number and I didn't. So I'll have to think about that one later. So that's a tricky one. But I did once challenge this to a high school student who came up with his own rather complicated algorithm that he can do, and he's just shown that he can do it better than I can. So yeah, in the back. Oh, thank you for asking. Okay, the missing digit trick. This one I can explain. And in fact, I bet there were some math majors in the audience who figured it out, so I'm going to give you a chance to show off. Remember when I had everyone take 3249, multiply by a 3-digit number? I told you what the missing number was. All right, finish my sentence. Oh, that one. That was all based on the magic property of the number 9. 9. 3 a little bit, but 9 much more so. What does 9 have to do with it? What do we know? Here I'm going to write down all the multiples of 9 that I can fit here. And what do the multiples of 9 have in common? They add up to 9, right? When you add the digits, you get 9. 1 plus 8 is 9. 2 plus 7 is 9. 6 plus 3 is 9. Wait, I see one exception there. 99. That adds up to 18, but that's okay because 18 is a multiple of 9. So here's the deal. A number is a multiple of 9 if and only if, when you add the digits, you either get 9 or 18 or 27 or 36. They always add to a multiple of 9. Now, if you remember at the beginning of the show, I said, let's take the last number on the board here, 3249. I didn't choose it because it was the last number on the board. That was just a convenient excuse. I chose it because it was, and still is, a multiple of 9, right? 3249 adds up to 18, so it's a multiple of 9. And none of the other numbers would work. 5776 adds up to 25. This adds up to 31. This one adds up to 22. None of those worked. And I know, was I lucky? Not terribly lucky, because where did those numbers come from? They were squares of 2-digit numbers. And if you had given me a multiple of 3, then when you square it, you'd get a multiple of 9. Every number is about a 1 in 3 chance of getting a multiple of 3, and when you square it, you'll get a multiple of 9. So with 4 numbers, I've got a pretty good chance, like an 80% chance, of getting a multiple of 9 up here. If I don't get a multiple of 9 up here, I don't have to do the trick. So, not in my contract, or I'll find some other clever way of forcing a multiple of 9. But anyway, 3249. So what did you do? If you have a calculator, you can still take 3249, multiply it by a 3-digit number. You'll get an answer that's either 6 digits or 7 digits. Anybody do that? Take 3249 times a 3-digit number. All right, go ahead, you can do it. And take, and you're going to get a 6-digit or 7-digit answer. How many digits do you have? 6? Okay, quickly give me 5 of your 6 digits. 1, 2, 4, 5, and one more number. 0. Okay. So he's got a 6-digit number, and I don't know what it is. I still don't know what it is, but I do know this. His 6-digit number has to be a multiple of 9, right? Because he started with a multiple of 9, and then he multiplied it by something. So the answer still has to be a multiple of 9. So what am I doing as he's calling out his 5 numbers? Adding them up. Let's see, 1 plus 2 is 3, plus 4 is 7, plus 5 is 12, plus 0 is 12. So what did he have to leave out in order to reach a multiple of 9? 6 in order to get to 18. Did you leave out a 6, sir? Yeah, good thing. So let's say he called out his numbers and they added up to 20. Then what did he leave out? 7 in order to reach 27. Suppose he called out his numbers and they added up to 27. Then what did he leave out? 0 or 9. You don't know. You don't know if those numbers add up to 27 or if the numbers add up to 36. So what do you do in that situation? You guess. Exactly. But as a magician, you can do it in such a way that it does not look like guessing. And in fact, that's what I did up here. Remember those two people? I said, I'm having some trouble with yours. Let me get back to you. I finally got back to them. I said, concentrate. I'm getting a lot of nothing. I say, which of you left out a 0, right? They both did. Perfect. I take my bow. If one of them did, I say, just you. I say, well, no wonder I was getting a lot of nothing from you. Okay, 0, got it. All right, but wait, yours, you didn't leave out a 0. Okay, concentrate harder. You left out the 9. Yes, okay. Or if I say, which of you left out a 0, and they say nothing, neither of them, I go, that's really strange. Unless you're canceling each other's thoughts. Did you both leave out the number 9? They go, yes, and you take your bow. Either way, it looks like you got it right. So that's, magicians call that having an out, whatever. If that's a little too sleazy for you, there's a slightly more honest approach you can say. Like, pretend you just left out a 0 or a 9, and I say, ooh, this is interesting. I see a couple possibilities. Tell me, did you leave out an odd number or an even number? And now if she says it's odd, you know she left out the 9. If she says it's even, or a look of panic goes across the face, because they don't know if 0 is even or odd or what, I'll see that look of panic. I'll go, you left out the 0, right? And you take your bow. So, slightly more honest. Thank you very much. All right. Let me take 1 or 2 more questions, then I'll launch into my grand finale. Yes, what's your question?
When did you start practicing mathematics?
Yes, when I said it, very good for saying that. It was really 2 separate loves. As a kid, I both loved playing with numbers and I enjoyed finding new ways of doing calculations. It was just a game for me. And I loved the fact that you could take a problem, do it lots and lots of different ways, and if you were careful, you'd always get the same answer. And I just thought that was really cool, and I still do today, not just with arithmetic, but all kinds of math. Wow, the Pythagorean theorem is really true. Here are 100 different ways you can see that it's really true. I think that's pretty cool. And as a kid, magic, I just love showing off. I outgrew that eventually, but as a kid, I liked showing off, and so eventually I did magic shows for kids' parties. I was the great Benjamini performing throughout the east side of Cleveland, and eventually I started doing shows for older audiences, and my father said, why don't you put some of that number stuff in the show? And I tried it, and to my surprise, it got a big reaction. So ever since then, since about college days, I've been doing this mixture of math and magic, and it seems to get people seem to like it. So that's, other questions? What else? Let me, yeah, please.
Going back to that one,
Yeah.
does it matter if you multiply by a 3-digit number?
It could have been any size.
Any size?
Any size, because the answer will still be a multiple of 9. Now, there's a reason I don't have them multiply it by a larger number than that, is because if they wind up with an 8-digit answer or bigger, there's a good chance that they will make a mistake as they're calling out their numbers. They're only psychologically, we can only hold on to about 7 numbers confidently. So I don't want the product to get too big, otherwise they'll make a mistake, but it'll seem like I made a mistake. So I don't want, but it could be any, if you don't want to do, if you want to start with a 3-digit number, like 324, multiply it by a 2-digit or a 3-digit number, you can get the product smaller. It just seems impressive, though, if the answer is 6 or 7 digits long. So, okay, so yeah, please.
What does it look like in your head?
Yeah, so what's going on in my head? And this is a great question towards my finale. 2 things. First of all, maybe to your surprise, I am not visualizing anything. So for me, this is completely an auditory process, not a visual one. In fact, I would say my spatial reasoning ability, my visualization ability is really rather average. But for example, when I work with numbers, I'm hearing them more than seeing them. Like if I said to you, what's 3 billion plus 4 billion, you say 7 billion. Not because you saw the 3 with 9 zeros and the 4 with 9 zeros and added them up that way. Rather, in your auditory memory, you know that 3 plus 4 is 7, and the word billion comes for the ride. That's what I'm doing as I'm adding the numbers very gradually. Now, eventually, I run into some memory limitations, and let me just very quickly show you something. And those in the audience who like words more than numbers, this will be maybe your favorite part of the show, is I use a phonetic code that allows me to turn numbers into words as a temporary storage device. So for example, the 1 is the T or the D sound, the T or D sound. The 2 is the N sound. The 3 is the M sound. And this is not my invention. This code's been around for a couple hundred years. And there are even nice mnemonics for remembering it. Like a T has 1 downstroke, and N has 2 downstrokes, and M has 3 downstrokes. 4 ends in R. 5, you can see the L over there, and so on. So there are tricks for memorizing the code. Once you have that memorized, you can take numbers, even phone numbers, credit card numbers. Here, somebody give me their credit card number. No exam. All right, so fine. Let me show you. Let's take a random number like the digits of pi. Okay, so, and anyway, I could give you 100 digits there, but I won't. And here is the method I use for memorizing pi or other random numbers. So let's say you had to hold on to this number in your head. All right? Let's do it in small doses. Take 314, first 3 digits. Now 3 is an M, 1 is a T, 4 is an R, and now you can place vowel sounds wherever you'd like. So what words could we create out of 314? Words like motor or meter or matter. Even matter, which is spelled with 2 T's, the T sound only happens once. So spelling doesn't matter in this code. All right, so those are the, so here, let's do 2 more digits. So I've got 1 is another T, 5 is a L, and so the first 5 digits of pi for me becomes my turtle. My turtle. And my turtle can only be turned back using this code into 31415. If you have the time to look at more and more digits, you can actually create sentences out of them. Here, let me give you the first 24 digits here. Let's see. Okay, so the first 24 digits becomes, my turtle Pancho will, my love, pick up my new mover Ginger. My turtle Pancho will, my love, pick up my new mover Ginger. Say that sentence 5 times and you'll unfortunately have it memorized. But with that, you'd have, if you know your code, the first 24 digits of pi. The next 17 digits, which start 338 or MMV, becomes my movie monkey plays in a favorite bucket, followed by ship my puppy Michael to Sullivan's back rubber. That gives you 60 digits of pi. If I wanted another 40, I won't write them down, but I'll give you their sentences. They are a really open music video, cheers Jenny F. Jones, followed by have a baby fish knife so Marvin will marinate the goose chick. Thank you very much. Now I don't know about you, but speaking for all the mathematicians in the audience, I can't look at a beautiful number like pi and resist the urge to break it to song. So I would like to share with you, just before I do my grand finale, and I still want to do that for you, I want to share with you a song I wrote a couple years ago on Pi Day, March 14th, to celebrate one of my favorite numbers. I'm only going to sing it once, though, because pi does not repeat. Right, so here. And thank you. A long, long time ago, I can still remember how my math class used to make me snore. 'Cause every number we would meet would terminate or just repeat. But maybe there were numbers that did more. But then my teacher said, I dare ya to try to find the circle's area. Despite my every action, I couldn't find a fraction. I can't remember if I cried the more I tried or circumscribed. But something touched me deep inside the day I learned of pi. Oh, pi, mathematical pi. Twice 11 over 7 is a mighty fine try. A good old fraction you may hope to supply, but the decimal expansion won't die. Decimal expansion won't die. Pi, mathematical pi. 3.14159265358 A good old fraction you may hope to define, but the decimal expansion won't die. Thank you. All right. If there are no more questions besides why am I speaking into a magic marker, I don't know. All right, one more question, then I'll launch into my grand finale. Yes?
What's your verbal mnemonic for E?
For E, you know, I guess because E was so regular, I mean, you got the 2.7, Andrew Jackson, which is frankly the way I remember that Andrew Jackson was elected in 1828, then the other way around, but there it is. And then I got isosceles right triangle, 45, 90, 45, and I've never really made a sentence beyond that just because that's all, you know, those were so easy to remember. So memorized with ease, what can I say? Okay, so let me wrap things up by doing something I promised you earlier. I'm going to try to square a 5-digit number and to really see what's going on in my head. But to make my job more interesting for you as well as for me, I'm going to do this last problem thinking out loud. So you can actually really hear what's going on while I'm doing a problem of this size. To make it more, let's choose a 5-digit number at random. How about this row here? If I can get 5 of you to each call out a number, that'll be my 5-digit number. 7. 5, 8, 3, 1. 75,831 squared. Yuck. Let me explain to you how I'm going to attempt this problem. I'm going to break the problem down into 3 parts. I'll do 75,000 squared plus 831 squared plus 75,000 times 831 times 2. Add all those numbers together, and with any luck, arrive at the answer. Now let me recap. Thank you. While I explain something else. As I do this last calculation, yeah, that's all you're going to remember from the talk. I got to use that one. All right. As I do this calculation, you're going to hear some words creeping into the calculation. You know what I'm doing now. I'm using the phonetic code that I showed you earlier. That's why I left these numbers here as a guide. One last suggestion for those of you with answers. Now, who's got an answer? Raise your hand. A few of you should have a 10-digit answer, beginning with 5, ending with 1. In between, I don't know yet. There's a 50% chance that I'll make a mistake somewhere in the middle. If I do, don't tell me what the mistake is. Just say you're close or something, and I'll try and figure it out, which can be pretty entertaining in itself. If, however, I am right, whatever you do, don't keep it to yourselves. Make sure everybody knows that the answer's right, because this is my big finish, okay? So without any more stalling, here we Go. I'll start the problem in the middle with 75 times 831 times 2. Now, 75 times 2 is 150. I'll take advantage of that. 150 is 3 times 5. 831 times 3 is 2493. 2493 times 5 is 12,465 times 10 is 124,650. 124,650 becomes tenor jails. Tenor jails is 124. That's tenor jails 650. Okay, haven't said any part of my answer yet, but I'm about to. Tenor jails. Next, I do 75 squared, which we can do is 5625. So I get 5 billion. Take the 625, add that to tenor. 625 plus 124 is 749, but I see a carry coming, so I'm going to say 750 million. Jails, jails. Okay, finally we do 831 squared. That's 800 times 862 plus 31 squared is 608. Oh gosh, I've got to make sure I get this one right. 689,600 plus 961. Is that really right? 689,600 plus 961 is 690,561. Leash it if I need it. Leash it. Take the 690, add that to jails. Oh gosh, to get 340,561. Good. Thank you very much. I hope you enjoyed Mathemagics. I'm Arthur Benjamin. Thank you. Thank you. If you have any more questions, I'll hang out for as long as you want me to answer your questions one-on-one. Thanks again.